how to perform a heat equation problem that covers a substance also going through a change of state of matter. Because we know from our heat equation, which is heat or energy or calories or joules, all the same thing, equals mass of the object or the substance times the specific heat value times delta T, which is a fancy way of saying temperature change. Okay, so if we're talking about raising water from 30 degrees Celsius to 60 degrees Celsius, then we know that because water freezes or melts at 0 degrees Celsius and it boils, vaporizes, or condenses back into a liquid at 100 degrees Celsius, if we're going from 30 to 60, we know that water is not going to experience a change of state in that change from 30 degrees Celsius to 60 degrees Celsius. So we don't have to worry about the extra energy required for water to make a change of state. All we have to do is worry about a temperature change within the same state, which at that point water would be a liquid. Okay? However, when substances, elements, compounds, whatever it might be that you're dealing with, when they go from being a solid, like let's say ice, and you heat it to where it melts, then it becomes water as a liquid or aqueous solution. And let's take it on up even farther to where it boils, then it becomes steam. There is a plateau at the melting and freezing temperature of water, which is 0 degrees, where this is a heating curve. You've probably seen this in lab. Okay, so you're using this amount of energy to raise ice from one temperature to another temperature in ice form. When ice begins to melt and turn into water, there is more energy needed to make that ice melt and change states of matter from a solid to a liquid than there is simply to heat it up with it staying in the same state. And when something is going from a solid to a liquid or a liquid to a solid, that heat or that level of energy is called heat of fusion. Something goes from a solid to a liquid or from a liquid to a solid due to a temperature change. Let's not even talk about pressure changes right now, because that throws another aspect in. We don't even need to talk about that. But if you're changing the temperature of something, it goes from a liquid to a solid or a solid to a liquid, then as it converts from one state to the other, there is an energy function there called the heat of fusion. Okay? Now, let's say that your water melts and you continue on up the heating curve until you get to 100 degrees Celsius. That is where water begins to boil. Okay? There's another plateau at that point. That is called the heat of vaporization. That is the lump sum of energy required to cause a substance to change from a liquid to a gas, or a gas back to a liquid. And there's also a plateau in your heating curve there. So let's create a sample problem, and we're going to say that we're going to take, let's just write the question out. How much energy in calories is needed to raise 10 grams of distilled water from negative 10 degrees Celsius to 120 degrees Celsius. Okay? So, we know from the framework of this problem, we know that the melting point of water, or the freezing point, is 0 degrees Celsius, and the boiling point is 100 degrees Celsius. We're going from negative 10 to 120 degrees Celsius. So we know that there are going to be changes in states of matter along the way. I would not expect your professor to give you this kind of a question on a lecture test, but you're probably going to be dealing with this in lab. I have seen several students working on this heating curve. And with the exception of water, if it was a different substance and they were asking you to do that, you would need to know the melting and the boiling point. It's different for alcohol, it's different for ethanol, it's different for cough syrup, it's different for gasoline. Okay, every substance has a heat of fusion and a heat of vaporization value to make it go from one state to another or one state to another on the high end. And those are all listed. There's probably chemistry references that will show that for thousands and thousands of different elements and compounds and other substances, okay? So you would be expected to be given that information. Just so happens we all know that water melts at 0 degrees and freezes at 0 degrees and boils or recondenses at 100 degrees. So let's look at how much energy is needed to raise 10 grams of water from negative 10 degrees Celsius to 120 degrees Celsius. Okay, so negative 10 degrees Celsius, we're starting out as ice, correct? Okay. We know that water melts from ice back into a liquid, from a solid to a liquid, at 0 degrees. So this first leg of the journey in this rise of temperature is going to take you up to the 0 mark. For that stretch, we simply use the heat equation. So the energy in calories is equal to mass times specific heat value for water times temperature change between the beginning point and that first plateau where the heat of fusion is, okay? So we insert, simply plug and play, 10 grams times 1.00 calories per gram per degree Celsius times a grand total for this leg of 10 degrees Celsius change. Simple multiplication gives us the answer of 100 calories. Now we encounter our first change of state of matter. When it hits 0 degrees, the ice is going to begin to melt. At that point, there is more energy needed to convert it from one state of matter to another state of matter than there is to simply raise the temperature. So at that point, we don't worry about delta T. Delta T is out of the picture. There is no temperature change to be considered as the ice is melting. It can be 0 degrees as water, it can be 0 degrees as ice. That point, that fence line, you don't worry about delta T, but you do have to know that the heat of fusion, the energy required to make water change states of matter, is 80 calories per gram of water. And we know from our problem that we're dealing with 10 grams of water. So to make water go from ice to a liquid, we know that it's going to take 80 calories per gram, and we have 10 grams. So now we know that we're going to use 80 calories as the ice melts. Okay, now we're in liquid form. We're back to water. So we've got a long way to go from 0 all the way to 100 degrees Celsius. For that transition from 0 to 100 degrees Celsius, water is going to stay in the same state. It's going to be a liquid the whole time until it gets to 100 degrees. So for this leg of the journey, once again, we're going to go back to the heat equation, which is going to incorporate the specific heat value, the number of grams of water and the temperature change, or delta T, in degrees Celsius. I wrote Fahrenheit. Okay, do the multiplication. You come up with 1,000 calories to make 10 grams of water go from a 0-degree liquid to a 100-degree liquid Celsius. When we get to that boiling point, we reach another plateau in our heating curve. Okay? And that plateau is now called the heat of vaporization. Because we're liquid, we're now going to vaporize into steam. But once again, it takes a larger abundance of energy to kick it over from a liquid to steam than it does to simply raise the temperature of the liquid. So we have to use another value called the heat of vaporization value for water. And that value is 540 calories per gram of water. So once again, we do the math. Temperature change is not an issue here because you're stuck at 100 degrees Celsius going from a liquid to a gas. So energy in calories is equal to 10 grams times 540 calories per gram. That's our heat of vaporization value. That equals 5,400 calories. Okay, so now we're here. Now, our problem states that we're going all the way up to 120 degrees Celsius. So as this boils off the steam, now we're going up to 120. Once again, we are raising the temperature of a substance, but it's not changing states of matter. It's steam at the start, steam at the finish. Okay? So we go back to the significant, specific heat value. Excuse me. Too many SHs. Specific heat value, just like we did on this diagonal journey and this diagonal journey. And now we're going in steam from 100 to 120. So we go back to our heat formula, which is 10 grams times 1 calorie per gram per degree Celsius times 20 degrees. We're going from 100 degree steam to 120 degree steam. 20 degree delta T for a grand total of 200 calories. Now, at the end of this problem, all you have to do, let's go back and let's make sure. We started at 10 degrees, we were ice. We went up to 0 degrees, we melted. That took a bunch of energy to melt. Okay? Then we were water, and we stayed in water all the way liquid, all the way up to 100 degrees Celsius. At that point, we were getting ready to convert over to steam. We had to use a whole bunch more energy again. And now, we went from steam at 100 degrees all the way up to 120. So we've gone from -10 to 120 with 2 state of matter changes involved. So we simply add the calorie energy values together in calories. 100 plus 80 plus 1,000 plus 5,400 plus 2,000, plus 200, excuse me, for a grand total of 6,600 calories to raise 10 grams of distilled water from -10 degrees Celsius to 120 degrees Celsius with 2 changes in states of matter along the way. Now just remember, every substance will have its own heat of fusion value and heat of vaporization value. I know the heat of fusion from water as being 80 calories and the heat of vaporization of water as being 540 calories. I only know those because I've got the book sitting open right here next to me. I don't quote me, but I don't think that any professor realistically is going to throw you a problem like this and then expect you to know that this is 80 cals and this is 540 cals, okay? Unless they specifically say in their lecture notes, hey, we want you to know this because you might see that on the test. I don't think you're going to see it. The reason I posted this video is because I wanted you all to understand that there is a difference between using the heat equation to raise the temperature of a substance in its current state. There's a difference between that and the amount of energy required to make it kick over from a solid to a liquid or liquid to a gas or vice versa.